All right, hello and welcome back, everyone. Today I'm going to be taking you through the weekly exam problems for the start of the term. So this is the first week back after the term one holidays. So what we're going to be looking at today is one exam problem from the 2023 exam. I believe this was the tech-free exam. So try and do this without technology if you can. So starting out, we've got here, basically it's a three-part problem from the 2023 exam. It was one of the last problems on the exam, and it relates to calculus. So here we're interested in the derivative. So it starts out here, it says that the shapes of two walking tracks are shown below. Here's a picture of those walking tracks, and we're told that track 1 is defined by this particular function, and track 2 is defined by this function. And the first thing that we need to work out is the values of a and b in each of those two equations. So question 1 should be relatively straightforward. It's a substitution question. So we need to take each of those equations that we've been given, and we're going to substitute in the values. So where it says f0 is equal to 12, that means we want to replace x in function f with 0, and that should give us the value of 12. So if we go ahead and substitute that in, we're going to get a minus 0 multiplied by 0 minus 2 squared. So what I've done here is I have taken this equation right here, and I've replaced x with 0, and this is what we get. And we can see once we do that, we're basically getting a take away 0 times something, and of course 0 times anything is just 0, so that's just going to leave us with a. So we can see here on the left hand side we have 12, and on the right hand side we have a, so therefore a is just equal to 12. So that was pretty easy. Let's do the same thing with g. So we're going to substitute in 1 into the function g, and this is going to give us 9. So this is using the other initial condition. If we go ahead and do that, we're going to get, if we replace x in this equation, so the second equation, with 1, we're going to get 12 times 1 plus b times 1 squared. 1 squared is, of course, just 1, so this will give us 12 plus b, and we can see that that's equal to 9. So in order to solve for b, we're just going to have to use a little bit of our algebra knowledge, subtract both sides by 12, and we're going to get that b is equal to negative 3, and these are, of course, the values that we were trying to find here. So we have successfully found each of the values correctly. All right, so moving on. Now we're told something about the turning point. So we're told that f and g both have a turning point at the same point on the graph. So that's this point right here. We can see that that's a maximum turning point. And as we can see, that point exists on both of the two curves. So it's kind of two parts to this question. We need to first up verify that they both have turning points at the same x coordinates, and then verify that their y coordinates are the same, which is to say we need to verify that the two lines both intersect at that point and also have a turning point at that point. So first up, whenever you have any question that relates to turning points, you should immediately be thinking derivative. Specifically, the derivative should be equal to 0, right? So at a turning point, we can see that the gradient is 0, so we need to make the gradient of each of these two equations equal to 0. So first up, let's just remind ourselves what our equations actually are. So the equation f, if I just take the value of a equals 12 and substitute it into the equation we've been given, we have this expression here for f, and we have the expression for g. We can get that by substituting in b is equal to negative 3 into this expression. Sorry, that would be, so b equals negative 3, and we have x squared, okay? So that's based on the initial conditions that we were given in part A. We have these two expressions. Now we want to find the derivative of each of these functions. So first up, just with the function f, I'm just going to expand those brackets there, just so I can apply the power rule of differentiation. So first up, I'm going to expand this perfect square over here. Okay, and then we can just expand those brackets. So this will give us 12 minus x cubed plus 4x squared minus 4x. Just be really careful here. What I've done is I've expanded, so first up I've expanded that perfect square, so the x minus 2 squared. X minus 2 squared. That was, if you want to expand it using FOIL, you could do so like this, or you can recognize that as a perfect square. Either way, that's how I got the x squared minus 4x plus 4 part of this expression. And then the second thing that I did was expand this negative sign that was out the front. And when you're expanding, multiplying everything by negative x, just remember to switch the sign of each term. So that's why this term went from a negative to a plus, this one went from a plus to a negative. So that's something you need to be really careful about, because a lot of people make mistakes with that. Okay, so now we're going to find the derivatives of both f and g. So let's sort of start a new line here to show that this is kind of the next step of working out. And I'll just use a different color for this. To find the derivative, we are going to try and apply the power rule. So first up, let's just go term by term with function f. The derivative of 12 is just 0, so we don't need to worry about that. The derivative of negative x cubed is going to be, now the negative sign will stay here. We bring the 3 at the front, and the x gets raised to 1 less power, so the power counts down. That's how the power rule works. Okay, let's move on to the next term here. We have 4x squared, so the 2 is going to come out the front. The power of x is going to count down by 1, and the coefficient will be 2 times 4, so that's going to be 8x. And then over here, the power counts down by 1. We're multiplying the coefficient by 1. That's not going to change anything. We just have minus 4 at the front there. Okay, so now we need to see if we can factorize this. We've got a quadratic. Just remember, when we're trying to find the turning point, that's when the derivative is equal to 0. So we are trying to find when f of x is equal to 0. So let's see if we can factorize this quadratic here. The way that we're going to do that is we're going to take the first and last terms, multiply them together. That is negative 3 times negative 4, which makes positive 12. And what we are going to be thinking about right now is what are two numbers that add to give 8 and multiply to give 12. So I'm thinking that's probably going to be 2 and 6. So we're going to split the central term in this little expansion here into 2 and 6. There we go. So you can see the first line there is equal to the second line. We've just split up that 8x into 2x plus 6x, right? And now what I'm going to do is I'm going to factorize the two halves of the quadratic. So first up, the first half of that quadratic, we're going to look at that. We can see that they both have both the terms have a common factor of x, so we're going to take out that x. That leaves us with negative 3x plus 2. And then if I look at the second half of the quadratic, okay, I can see that they have a common factor of 2. So let's take out that common factor. That leaves us with, sorry, that's not right. Let's just go back. So edit, undo, edit, undo. Okay, let's try that again. Give me a minute, just trying to use this pen properly. Oh. Smooth. Okay, let's try that again. So, okay, once I take out that common factor of 2, what are we left with? Well, first up, I'm actually going to take out a common factor of negative 2, aren't I? Because I want the thing in the brackets over here to be the same as the thing in the brackets over here. So if I take out a common factor of negative 2, let's just see what happens to each of these terms. So we have 6x divided by negative 2, that's equal to 3x, right? And then the second term, the term at the end here, is going to be negative 4 divided by negative 2, which is going to be plus 2. So that's a negative divided by a negative, which makes a positive. Okay, so strategically, I have made it so that both of these two things in the brackets are the same, and therefore we can factorize this and find that this is the same as x minus 2 negative 3x plus 2, which means that, because we want this to be equal to 0 based on the null factor law, x must be equal to 2 or x must be equal to, if we solve this thing for 0 here, so I'm thinking, I'll just do this over here, 3x plus 2 equals 0. How we do that would be, maybe we can make both sides, so add 3x to both sides. That's going to give us 3x equals 2, and therefore x is equal to 3 on 2. So that's how we get this other solution of, so that's 2 over 3, other way around. Okay, so those are our two solutions there for the function f. Okay. So the two solutions are x equals 2 and x equals 2 over 3. Okay, thankfully g is significantly easier than that to derive. So let's start out with the derivative of g of x. First up, we're going to look at 12x. If we take the derivative of that, the power counts down by 1, so this is going to become x to the power of 0, and this will simply become 12. And then over here, we're going to have negative 3x squared, so if we take the derivative of that, the 2 gets multiplied by the 3, so this becomes negative 6x. The power counts down by 1. Now, when's that equal to 0? Well, let's just think about this. This is just a two-step linear equation. Should be pretty straightforward to solve. We're going to add 6x to both sides, and then we're going to divide both sides by 6, and that's going to give us 12 divided by 6, that's equal to 2. Okay, so what we're seeing here now is that both of them have a solution at x equals 2. So what that's telling us is that both f and g have a derivative at that point, so that implies that they both have a turning point at the point x equals 2. Which is halfway to proving what we want to show. We, of course, also want to show not just that the two functions have a turning point at that point, but we also want to show that they're both equal to the same y value, which is to say that they intercept at that point. So how do we do that? Well, we're going to have to substitute in x equals 2 into both functions f and g and make sure that they're both equal to the same thing. So let's do that. We're going to take the value of 2, the function f when x is equal to 2. Just remember that that function is written up the top here. So I'm going to substitute in 2. We're going to get 12 minus 2 times 2 minus 2 squared. Now 2 minus 2 is just equal to 0, so we're going to get this is just equal to 12. And meanwhile, if I substitute in x equals 2 into the function g, what are we going to get? Well, we're going to get 12 times 2, take away 3 times 2 squared. Now, 2 squared is just equal to 4. So this is going to be equal to 24 minus 3 times 4, which is 12, which is equal to 12. So we can see that both f and g are equal to 12 at this point, which is to say that they are both equal to the same y value at this point. And specifically, we can now conclude, let's just put our answer somewhere. It's a little bit messy now, but we can conclude that the coordinates of P, so remember to double read the question at the end. Have we answered it? What is the coordinates of the point P? Well, we know that the x-coordinate is 2, the y-coordinate is 12, because they're both equal to that same value, and therefore we can conclude that P is going to be equal to 12. So that's the answer to the question. So x is 2, y is 12 for both of the functions, and as we can see, that is indeed a turning point because we found that the derivative is equal to 0 there. So there's quite a bit to that question, but yeah, that's the kind of stuff that you need to include. This is kind of like the minimum amount of information, I guess. The absolute minimum is finding the derivative equal to 0, finding that they both have x equals 2, and then confirming that that value works for both equations. Something else that you could have done here is if you wanted to verify that they both had the same coordinates at that point, is you could have actually just made fx equal to g of x and then solved for x. This would have been another way of doing it, but you would have also needed to verify that whatever x value you got, so you would have found x equals 2 if you did that, you would have needed to verify that that is indeed a turning point. So either way, you would need to find the derivative. So keep that in mind. Okay, so moving on to the last question here, we have a little bit of a context. It says a theme park is planned with boundaries which form a triangle. The triangle goes from O to A to B. So it's this little triangle here in the diagram, right? So that's being given to us. Where O is the origin, so that means that O has the coordinates 0, 0. The point A over here, that has the coordinates K, 0. And then the point B has the coordinates of K and whatever G is equal to at the point K. Okay, so let's just consider this triangle here for a minute before we move on with the question. What do we know about this triangle? Well, the distance from here to here, we can see is just K, right? So that's the distance from 0 to K. So the length of that is K kilometers. Just remember, I said earlier that all of the units are given to us in kilometers, so that's K kilometers. And then this here is the value of K, so the value of G at the
point k. And given that we're going to need to know that function, let's just remind ourselves of the function g. We had it up here, so gk is going to be equal to 12k minus 3k squared. That's just substituting in x equals k into g of x. Okay, so that's what we know. Now, the question's asking us, what is the maximum possible area of the theme park in kilometers squared? So we're dealing with a triangle. We just need to remind ourselves what the formula for the area of a triangle is before we answer this question. So we all should know that the area of a triangle is given by half base times height, not squared. I don't know where that came from, but it's just half base times height for the area of a triangle. So we can see we know what the height is, that's gk, and we know what the base length is, that's k. So we can just go ahead and write an expression for area in terms of these variables. We have half times the base length of k times 12k minus 3k squared. And we can also just go ahead and expand those brackets. So if we multiply everybody by half k, this is going to give us 6k squared, take away 3 over 2k cubed. That is an expression for A. Now, we're trying to find maximum area. So whenever we're dealing with maxima and minima, just like when we have something to do with turning points, we should immediately be thinking derivatives. So remember, the maximum area will occur at the turning point, which is when the derivative is equal to 0. So in this case, what we're actually finding is the derivative of A with respect to K. So make sure your notation is correct here. We're finding the derivative of A with respect to K. So we write dA dk, and then we apply the power rule to that derivative, just like we did before. That's going to give us, so the 2 comes out front, so that's 12 times K, take away 9 over 2K squared. So that's just deriving this expression that we have right here. Now, we want to know, when is this equal to 0? So how do we find that? Well, we can see if we can factorize this just a little bit. Also, just remember, if we one side's equal to 0, right? It doesn't matter what we do to that side. So just to tidy things up, I'm just going to multiply both sides by 2. So on the left-hand side, I'm going to get 2 times 0, so it's just still 0. And on the right-hand side, I'm going to get 24k take away 9k squared. That just allows me to get rid of that ugly half there. So we've got 24k minus 9k squared. And if I try and factorize that real quick, we can see that there's a common factor of k to both terms. There is also a common factor of 3 to both terms. So we can take out 3k, that leaves us with 8 minus 3k as our factor on the inside there. So what I've done there is I've gone 24 divided by 3 is equal to 8, taken out that common factor of 3k, written it out the front here, and that's left us with this factorization here. Now, when is this equal to 0? Well, looking at these two factors based on the null factor law, the derivative of a with respect to k will be equal to 0 when k is equal to 0, or when 8 minus 3k is equal to 0, right? So k equals 0, that's going to be the minimum. We can see here, if k is equal to 0, we actually don't really have a triangle. We've kind of just got like a point. So the area of that shape would, of course, just be equal to 0. So that must be the minimum. So what we want is the maximum. So that's the minimum, not interested in that. This would be the maximum. So if we solve this for k, we're going to find, well, we get 8 equals 3k if we plus 3k to both sides. And then if we divide both sides by 3, we get k is equal to 8 on 3. Okay, so that is our value of k. The question is asking us what the maximum area is. So find the maximum possible area of the park. So to find that, this is the maximum value of k. We need to take that value of k and substitute it back into our expression for area. So we can find that the maximum area, A max, is going to be equal to 6 times 8 on 3 squared, take away 3 on 2 times 8 on 3 cubed. And if this is a tech-free exam, we're going to have to come up with some way of solving this, because this is quite an ugly little expression involving some fractions. So we do need to find what this is. So let's see what we know about this. Well, hopefully everyone knows their square numbers for the numbers 1 through to 12. So we can see here that first up we have 8 squared. Just remember, if we have 8 over 3 squared, that's going to be equal to 8 squared divided by 3 squared. So 8 squared is 64. 3 squared is 9. Okay. This is what I get worried about. We have this cube over here. Can we simplify this a little bit? Well, something that we know about cubes is we could just break this up into 8 over 3 times 8 over 3 times 8 over 3. We could also write it as 8 over 3 times 8 over 3 squared. So we could write this as this, right? Like just using the fact that 8 over 3 cubed is going to be equal to 8 over 3 times 8 over 3 times 8 over 3, which means that's just equal to 8 over 3 times 8 over 3 squared, right? So that should be fine. That gives us what I've written down here. So 3 over 2 times 8 over 3 times 64 over 9. And then what we might notice is that we've got a 3 up here and a 3 down there. They're going to cancel out. And now both of these two terms have a common factor of 64 over 9. So I might just take that out the front here, 64 over 9. Taking that out, that leaves us with 6 for this first term. And 8 divided by 2, that's equal to 4. Taking out that common factor of 64 over 9. And we can see now we just have 64 over 9 times 6 minus 4, which is just equal to 2. 6 minus 4 is equal to 2. So therefore, we're going to get 2 times 64 over 9, which is equal to 128 over 9. And that is our maximum area, so we should include units in our final answer. So that is 128 over 9 kilometers squared, and it's perfectly fine to leave your answer as a fraction, provided that it is written in the simplest possible form. So 128 shares no common factors with 9, so you'll just leave your answer like that. Always good to go back at the end just to double check you've answered the question. Yep, so all we had to do here was find the maximum possible area. So we're done. That's the answer. All right, thank you very much for joining in today. Those are the solutions to those exam questions. I'll see you guys in the next video. Have a good one.